In October of 2017, a telescope on a mountain in Hawaii saw something that should not have been there. Something that came from a place no human instrument had ever touched, moving through our solar system like a messenger from the void itself. Welcome to the sleepy cosmos. Tonight we're exploring this strange rivalry between two visitors from beyond our star. There is a particular kind of silence that exists between the stars, a silence so profound that it makes the deepest ocean trench seem like a bustling city street, and into this silence, across distances that would take our fastest spacecraft tens of thousands of years to traverse, something had been falling for millions of years, tumbling through the nothing, spinning end over end through the cosmic dark, until one autumn day, it passed close enough to our sun that we could see it, could track its motion against the background of distant galaxies, could realize with a slow-building sense of wonder and unease that this object, whatever it was, had not been born here, had never orbited our star, had come from somewhere else entirely, from the space between the suns, from the true deep of the universe where no planet circles and no warmth reaches and nothing grows. The Pan-STARRS telescope, perched on the summit of Haleakala in Maui, was designed to scan the heavens for near-Earth objects, for asteroids and comets that might one day pose a threat to our world, and on the 19th of October in 2017, it found something in its automated images, a faint point of light moving against the stars. Nothing unusual at first, just another rock in space. Another piece of solar system debris, doing what such objects do. But as astronomers began to calculate its trajectory, to work out the mathematics of its path through the inner solar system, they realized something extraordinary, something that sent a ripple of excitement through the astronomical community, like a stone dropped into a still pond. This object was moving too fast, far too fast to be gravitationally bound to the sun, and its trajectory was not an ellipse, not the closed loop that captures planets and asteroids and comets in eternal circuits around our star, but a hyperbola, an open curve, the mathematical signature of something passing through, something that had come from elsewhere and was heading elsewhere still. A visitor, a wanderer, the first confirmed interstellar object ever detected, passing through our cosmic neighborhood. They named it Oumuamua, a Hawaiian word that means scout or messenger, the one who reaches out ahead, the one who arrives first from a distant place, and the name carried within it both poetry and precision. Because this object was indeed a scout, the first emissary from the galaxy beyond our solar system to be recognized as such, though surely countless others had passed through across the billions of years of Earth's existence, unseen and unrecorded, tumbling through the dark while dinosaurs walked below and mammals emerged, and humans eventually looked up and wondered what was out there beyond the sphere of wandering lights they called planets. The first images of Oumuamua were disappointing in the way that many first glimpses of cosmic wonders are disappointing not because the object itself was uninteresting, but because distance and the laws of optics conspire to reduce even the most exotic visitor to a faint dot, a barely perceptible smudge against the darkness. And as astronomers trained more powerful telescopes on this interloper, hoping to resolve its shape and surface features, they found that Oumuamua was already too far away, already receding from the sun at tremendous velocity, a guest who had arrived unannounced and was departing just as mysteriously, and all they could do was gather what light they could, measure its brightness as it rotated, analyze the spectrum of sunlight reflecting from its surface, and try to piece together a portrait of this stranger from the fragments of data streaming into their instruments. What emerged from this analysis was deeply strange, stranger perhaps than anyone had anticipated, because Oumuamua was not shaped like a typical asteroid or comet, not roughly spherical or potato-like as most small bodies in space tend to be, but elongated, stretched out like a cigar, or a needle, or perhaps a flattened disc seen edge-on, with a length-to-width ratio of at least 10:1, possibly more, making it one of the most extremely elongated objects ever observed in the solar system. And this shape alone was enough to spark curiosity and speculation, because nothing in our experience of asteroids and comets quite matched this geometry. This strange attenuated form that spoke of unusual formation conditions, or perhaps violent collisional history, or possibly, and here was where the speculation began to venture into territory, both thrilling and controversial, artificial construction. Though of course there was no evidence for that. No signal emanating from the object. No deviation from a trajectory explicable by gravity alone, just an unusual shape and the fertile ground of human imagination. But the shape was only the beginning of Oumuamua's mysteries, because as astronomers continued to track its motion through the solar system, refining their measurements, accounting for the gravitational influence of the sun and planets, they noticed something that did not fit the models, a tiny but measurable acceleration away from the sun, a gentle push that could not be explained by gravity alone. And this non-gravitational acceleration was reminiscent of the way comets behave when they approach the sun and their ices begin to sublimate, venting gas and dust into space in jets that act like tiny rocket engines, pushing the comet slightly off its purely gravitational trajectory. But Oumuamua showed no signs of cometary activity, no visible tail, no coma of gas and dust surrounding its nucleus, no spectroscopic evidence of the water vapor or carbon monoxide or carbon dioxide that typically streams from active comets. And yet something was pushing it. Something was imparting a small but undeniable acceleration that grew weaker as the object moved away from the sun, exactly as one would expect if sunlight itself were responsible, and this is where the conversation began to turn toward possibilities that seemed almost too exotic to credit. Sunlight carries momentum, a fact that seems counterintuitive because light seems so insubstantial, so ethereal. But photons, the particles of light, do indeed possess momentum despite having no mass, and when they strike an object and either bounce off or are absorbed, they transfer that momentum to the object, pushing it ever so slightly. And for most objects in space, this radiation pressure is negligible, far too weak to measure against the much stronger pull of gravity. But for an object that is very small, or very light, or crucially, very reflective, and very thin, radiation pressure can become significant, can produce measurable accelerations, and this possibility that Oumuamua might be thin enough or reflective enough for sunlight alone to push it off course led some scientists to propose that the object might be an incredibly flat disk, or perhaps even something artificially manufactured, a light sail from another civilization drifting through the galaxy like a piece of cosmic flotsam. And while this hypothesis was received with considerable skepticism by most astronomers, who preferred more conventional explanations involving outgassing of exotic ices that somehow did not produce a visible coma, the very fact that such a scenario was being seriously discussed in peer-reviewed scientific papers speaks to how genuinely puzzling Oumuamua was, how resistant it proved to easy categorization. Abraham Loeb, a respected astrophysicist at Harvard University and chair of the astronomy department, became one of the most prominent advocates for taking the artificial origin hypothesis seriously, not because he claimed to know that Oumuamua was an alien artifact, but because he argued that the possibility should not be dismissed without evidence, that science advances by considering all hypotheses that fit the data and then working to test them, and his willingness to publicly discuss the possibility that Oumuamua might be a probe or debris from an extraterrestrial civilization made him both celebrated and controversial. Celebrated by those who appreciated his openness to unconventional ideas, and controversial among colleagues who felt he was giving undue credence to a scenario that lacked supporting evidence and risked sensationalizing what was already a remarkable discovery, even if Oumuamua turned out to be entirely natural in origin. The debate over Oumuamua's nature and origin spread beyond the astronomical community into popular culture, into news articles and social media discussions, and late-night conversations between friends looking up at the stars, and for a moment the world was reminded that our solar system is not isolated, not a closed system floating in empty space, but part of a galaxy containing hundreds of billions of stars, many of them with their own planetary systems, their own asteroids and comets, and that material from those distant systems can and does occasionally pass through our neighborhood, carrying with it information about conditions in other parts of the galaxy, about the chemistry of distant stellar nebulae, about the processes that shape planetary systems light years away, and whether or not Oumuamua was artificial. Its very presence forced humanity to confront the reality that we live in a universe filled with such objects, most of them invisible to us, streaming through the space between planets on trajectories that only rarely bring them close enough to Earth for our telescopes to detect. The color of Oumuamua, measured through careful photometry as the object rotated, was reddish, similar to many objects in the outer solar system that have been irradiated by cosmic rays for billions of years, their surfaces slowly transformed by the impact of high-energy particles into organic compounds that give them that distinctive rusty hue, and this coloration suggested age, suggested that whatever Oumuamua was, it had been traveling through space for a very long time, exposed to the harsh environment of interstellar space, where there is no protective magnetosphere, no atmosphere to filter radiation, just the slow, steady bombardment of cosmic rays and the occasional impact of interstellar dust grains moving at speeds of tens of kilometers per second, each collision depositing energy, heating the surface momentarily, slowly eroding and altering the chemical composition of the object's outer layers. The rotation of Oumuamua was complex. Not a simple spin around a single axis like a spinning top or a thrown football, but a tumbling motion, a chaotic rotation that suggested the object was either irregularly shaped or had experienced some disrupting event that left it spinning in multiple directions simultaneously. And this tumbling behavior meant that the amount of sunlight reflecting from Oumuamua toward Earth varied dramatically over time, with the object brightening and dimming by a factor of 10 or more every few hours as different faces rotated into view. And from the pattern of these brightness variations, astronomers could infer constraints on the object's shape, though they could not determine it uniquely, could not say with certainty whether they were looking at an elongated cigar, a flattened pancake, or something even more irregular. By the time Oumuamua had been observed for a few weeks, it was already moving beyond the orbits of Mars and Jupiter, already too faint for even the largest telescopes to track, and it became clear that humanity had missed its chance to study this visitor in detail, that if only we had detected it a few weeks earlier, when it was closer to Earth, we might have been able to resolve its shape directly, might have been able to detect the composition of its surface through detailed spectroscopy, might even have been able to send a spacecraft to rendezvous with it, though such a mission would have required technology and preparation we did not possess, and so Oumuamua slipped away into the darkness, heading back out into interstellar space, its mysteries largely intact, leaving behind more questions than answers and a scientific community acutely aware that it had just experienced something unprecedented. And then, just 2 years later, it happened again. On the 30th of August, 2019, an amateur astronomer named Gennady Borisov, observing from his personal observatory in Crimea, using a telescope he had built himself, discovered what appeared to be a comet in the constellation of Cassiopeia, and like all good amateur astronomers who find something new, he reported his discovery to the Minor Planet Center, the international clearinghouse for observations of asteroids and comets, and within days professional astronomers around the world had begun following up on his observation, measuring the new comet's position, calculating its orbit, and once again, just as with Oumuamua, the mathematics revealed something extraordinary. This comet, too, was moving on a hyperbolic trajectory, too fast to be bound to the Sun, arriving from interstellar space and destined to return there, another visitor, another messenger, the second confirmed interstellar object ever detected, and it was given the designation 2I divided by Borisov, indicating that it was the second interstellar object discovered, bearing the name of its finder. But 2I divided by Borisov turned out to be quite different from Oumuamua in almost every way, and these differences would prove illuminating, would help astronomers understand what was typical and what was unusual about interstellar visitors, would provide context for the strange properties of the first object by giving them something to compare it against. Where Oumuamua had been mysterious and uncommunicative, revealing almost nothing about itself, 2I divided by Borisov was garrulous, obvious, displaying clear cometary activity with a prominent tail and coma that made its nature immediately apparent, and this was in many ways a relief to astronomers who had spent 2 years puzzling over Oumuamua, because here at last was an interstellar object that behaved in a comprehensible way, that looked and acted like comets from our own solar system, suggesting that whatever strange conditions had shaped Oumuamua, they were not universal, not characteristic of all objects drifting between the stars. The spectrum of 2I divided by Borisov, measured as sunlight passed through its coma and was filtered by the gases streaming from its nucleus, revealed the presence of cyanide compounds and diatomic carbon, molecules that are common in solar system comets, and that arise from the sublimation of frozen gases as the comet approaches the sun. And this chemical composition was reassuringly familiar, suggesting that the chemistry occurring in the planetary system where 2I divided by Borisov formed was not radically different from the chemistry that occurred in our own solar system billions of years ago, that the basic building blocks of matter, the elements and molecules that condense in the cold outer regions of stellar systems, are similar throughout the galaxy, or at least in our corner of it. But there was something unusual about 2I divided by Borisov as well. Something that set it apart from typical solar system comets and hinted at exotic origins. Its coma glowed with an unusual green color, more intense than most comets display, and this verdant hue was traced to an exceptionally high concentration of diatomic carbon, carbon molecules consisting of 2 carbon atoms bonded together, which fluoresce in sunlight at wavelengths that appear green to the human eye. And the amount of diatomic carbon in 2I divided by Borisov's coma was among the highest ever measured in any comet, suggesting that its parent planetary system might have had a different carbon to oxygen ratio than our own, or that it formed in a particularly carbon-rich environment, or that its thermal history was somehow different from typical solar system comets. As astronomers continued to observe 2I divided by Borisov through the fall of 2019, watching as it swung around the sun and began its journey back out into interstellar space, they noticed something else. Unusual. The comet was exceptionally rich in carbon monoxide relative to water, much more so than most solar system comets, which tend to be dominated by water ice with lesser amounts of other volatiles, and this high carbon monoxide abundance suggested that 2I divided by Borisov might have formed very far from its parent star, farther out than the regions where most solar system comets originated, in a zone so cold that even carbon monoxide, which only freezes at temperatures near absolute zero, could condense into ice and become incorporated into the comet's nucleus. Then something remarkable happened. Something that would provide yet another name for this object, and yet another layer of mystery to its story in late 2019. Several months after Gennady Borisov's initial discovery, an automated sky survey called ATLAS, the Asteroid Terrestrial Impact Last Alert System, operating telescopes in Hawaii, detected what appeared to be a new comet, and this object was given the provisional designation C, divided by 2019 Q4, but as more observations came in and its orbit was calculated more precisely, astronomers realized with surprise that this new comet was actually the same object as 2I divided by Borisov, and furthermore that it was indeed on an interstellar trajectory, and so the object received yet another designation, becoming 3I divided by Atlas in some databases due to a brief administrative confusion about whether it was the second or third confirmed interstellar object, depending on how one counted, preliminary detections that were later confirmed or ruled out. The designation confusion was eventually resolved, with the astronomical community settling on 2I divided by Borisov as the official name. But in the popular press and in some scientific discussions, the name 3I divided by Atlas persisted, became attached to discussions of the object's most unusual properties, particularly its strange carbon chemistry and green color. And so, in the public imagination, there emerged a sense of multiple interstellar visitors of Oumuamua and Borisov and Atlas, when in fact the latter two were the same object, seen by different telescopes and named according to different conventions. But this confusion itself speaks to something interesting about how we categorize and understand these visitors, how we struggle to fit them into our taxonomies, how each new piece of information seems to multiply rather than resolve the questions surrounding them. For the purposes of this story, we can think of 3I divided by Atlas and 2I divided by Borisov as two aspects of the same object, two names for a single comet that revealed itself differently to different observers, that appeared first to an amateur's telescope as a fuzzy spot of light in Cassiopeia, and then to an automated survey as a new detection requiring designation and study. And in both cases, what emerged was a picture of an object that was simultaneously familiar and alien. A comet that behaved like comets we know, but carried with it the chemical signature of a planetary system not our own. A place where the proportions of elements and molecules were subtly different, where the distances from the parent star and the temperatures in the outer reaches of that system conspired to produce an object whose composition was just exotic enough to reveal its foreign origin. Now we had two interstellar objects to compare, two data points where before we had none, and astronomers could begin to ask questions about what was typical and what was unusual, could start to build a statistical picture of the population of objects drifting through the galaxy between the stars, could estimate how many such visitors pass through the inner solar system each year undetected, could calculate how many might be comets, like 2I divided by Borisov, and how many might be inert, rocky, or metallic bodies like Oumuamua appeared to be, and could wonder what percentage might be even stranger, might defy categorization entirely, might force us to expand our vocabulary for describing what we find in the cosmos. The differences between Oumuamua and 2I divided by Borisov were striking and informative. Where Oumuamua was silent, inert, showing no cometary activity despite its close approach to the Sun, 2I divided by Borisov was vigorously active, its nucleus shedding gas and dust at rates comparable to solar system comets, creating a substantial coma and a long flowing tail that pointed away from the Sun like a windsock in a cosmic breeze. And this difference suggested that either the two objects had very different compositions, with Oumuamua perhaps being a rocky body that never contained much ice, or whose ices had all sublimated away during previous close approaches to other stars, or that they had different thermal histories, with Oumuamua perhaps being more thoroughly processed by heat and radiation over its lifetime, or possibly that Oumuamua's activity was simply too weak to detect, given how far it was from Earth when we first spotted it, and how quickly it passed through the inner solar system. The orbit of Oumuamua, traced backward in time using sophisticated models that account for the gravitational influence of all the major planets and the non-gravitational acceleration that so puzzled researchers, suggested that it had entered the solar system from the general direction of the constellation Lyra, from the approximate direction of the star Vega, though it had not come directly from Vega and had probably been traveling through interstellar space for millions of years, long enough that tracing its origin to any particular star system was impossible given the motions of stars around the galaxy and the uncertainties in measuring Oumuamua's trajectory, and so its birthplace remains unknown, remains one of countless stellar systems scattered across this region of the galactic disk, any one of which might have been the site where this strange elongated object was born, was ejected, was sent tumbling into the dark. The orbit of 2I divided by Borisov, similarly traced backward, suggested an origin from somewhere in the general direction of Cassiopeia, from a region of the sky where no particularly nearby stars reside, implying again a long journey of millions or tens of millions of years, enough time for the comet to have travelled across a substantial fraction of the distance between the spiral arms of the galaxy, enough time for its parent star to have moved significantly from wherever it was when this comet was ejected, and so, like Oumuamua, the precise origin of 2I divided by Borisov remains indeterminate, remains a mystery that may never be solved unless we eventually develop the capability to send probes that can catch up to these objects and study them directly, can place instruments on their surfaces and measure their properties in detail, and perhaps even sample their material for detailed laboratory analysis back on Earth. The speed of both objects was extraordinary by solar system standards, though modest by galactic standards. Oumuamua was travelling at roughly 26 kilometers per second relative to the Sun when it entered the solar system, before the Sun's gravity accelerated it to even higher speeds as it fell inward, and then decelerated it again as it climbed back out of the gravitational well. And 2I divided by Borisov was moving at roughly 32 kilometers per second relative to the local standard of rest, the average velocity of stars in our region of the galaxy, and these speeds are typical of objects that are not gravitationally bound to the Sun, but are instead participating in the general orbital motion of stars around the galactic center, each star and its attendant debris moving on its own, slightly different trajectory around the massive black hole at the heart of the Milky Way, and occasionally, just by chance, one star's lost comet or asteroid wanders into another star's sphere of influence and becomes briefly visible before continuing on its way. The question of how these objects became interstellar in the first place is itself a fascinating puzzle. Most astronomers believe that they were ejected from their parent planetary systems through gravitational interactions with giant planets, the same process that has scattered objects from our own solar system into the Oort cloud and occasionally sends them tumbling toward the Sun or flings them out into interstellar space entirely. And computer simulations of planetary system formation suggest that such ejections are common, that for every planet that settles into a stable orbit around its star, hundreds or thousands or even millions of smaller bodies are thrown out into the galaxy, becoming wanderers, exiles, objects unbound from the gravity of any sun. And over the billions of years since galaxies began forming stars, this process has populated the space between stars with an enormous number of such objects, far more than remain bound within planetary systems. The density of interstellar objects in the galaxy is difficult to estimate because we have only detected 2 of them so far, and from such a small sample, it is hard to extrapolate to the total population, but based on the rate at which Pan-STARRS and other sky surveys detect these objects, astronomers estimate that there might be thousands or even tens of thousands of interstellar objects larger than 100 meters in diameter passing through the inner solar system every year, most of them too faint or too fast-moving to be detected by current telescopes. And if this estimate is correct, then the space between stars is not empty at all, but rather is sparsely populated with debris from countless planetary systems, a kind of cosmic sea through which stars move like ships, occasionally sampling the material that drifts between them. The implications of this for our understanding of how planetary systems exchange material are profound. If interstellar objects are as common as these estimates suggest, then over the lifetime of a planetary system, billions of years, it will be visited by trillions of such objects, most of them passing through without incident, but a tiny fraction colliding with planets or moons, and each such collision delivers material from another stellar system, another chemistry, another set of formation conditions. And this means that the material that makes up Earth and the other planets may not all have originated in our own solar system, but may include small contributions from countless other systems, a kind of cosmic cross-pollination that means no planetary system is truly isolated, that we are all participants in a slow galactic mixing process that operates over timescales of billions of years. This idea connects to an old hypothesis called panspermia, the notion that life or its precursor molecules might be transported between planetary systems on asteroids or comets, that perhaps life on Earth did not arise here independently, but was seeded by material from elsewhere. And while most scientists remain skeptical that viable organisms could survive the harsh conditions of interstellar space for millions of years, the intense radiation, the extreme cold, the vacuum, it is at least conceivable that complex organic molecules could survive such a journey, molecules that might contribute to the chemistry of life in a new planetary system, even if they themselves are not alive. And the detection of interstellar objects like Oumuamua and 2I divided by Borisov makes this scenario seem less speculative and more like a natural consequence of the way matter is distributed and transported throughout the galaxy. The chemical composition of 2I divided by Borisov, with its high carbon monoxide content and its unusual carbon chemistry, provides a glimpse into the conditions in its parent planetary system, suggests that the region where it formed was both very cold and perhaps had a different elemental composition than our own solar system. And this is valuable information because it tells us that planetary systems, even those that form around stars similar to our Sun, can be quite diverse in their detailed properties, can produce comets with compositions that fall outside the range we see in our own system, and this diversity is exactly what one would predict if planetary systems form through chaotic processes that are sensitive to initial conditions, to the precise distribution of elements in the protoplanetary disk, to the timing and location of planet formation, to the dynamical interactions between planets as they migrate and settle into their final orbits. The green glow of 2I divided by Borisov, that eerie verdant light shining from its coma as it curved around the Sun, became one of its most distinctive features, something that captured the public imagination in a way that Oumuamua's cryptic silence had not quite managed, because here was something you could see in photographs, something that looked alien even though it was just a consequence of ordinary physics and chemistry, just the fluorescence of carbon molecules excited by sunlight. But there was something about that color, something unsettling and beautiful, that made the comet seem more real, more tangible, less like an abstraction in an astronomer's database and more like a visitor. You could almost reach out and touch if only your arm were long enough and you could survive the absolute cold of space. The tail of 2I divided by Borisov, streaming behind the comet for millions of kilometers as it rounded the Sun, was composed of dust and gas being driven away from the nucleus by the pressure of sunlight and by the solar wind, that constant stream of charged particles flowing outward from the Sun at speeds of hundreds of kilometers per second, and the structure of the tail, captured in multiple images as the comet passed through our neighborhood, showed complex patterns, streamers and knots and variations in brightness that reflected changes in the comet's activity level, perhaps triggered by localized jets on the nucleus as different regions of the surface were heated by sunlight and began to sublimate, releasing gas and dust in episodic bursts rather than in a steady stream. And then, just a few months after its closest approach to the Sun, 2I divided by Borisov did something that comets sometimes do, but that is always dramatic when it happens. It began to break apart, to fragment, and astronomers watching through the Hubble Space Telescope and other instruments observed what appeared to be pieces separating from the main nucleus, chunks of material that had been loosened by thermal stress, or perhaps by the release of gas from beneath the surface. And this fragmentation event provided a rare opportunity to study the interior composition of an interstellar comet, because the fresh surfaces exposed by the breakup would not yet have been processed by radiation and weathering, would reveal the pristine material from which the comet was made billions of years ago in some distant planetary system. The fragments of 2I divided by Borisov continued to move along roughly the same trajectory as the main nucleus, forming a kind of train of debris that slowly dispersed over the weeks and months following the fragmentation event, and eventually these pieces became too faint to detect and the comet faded from view, leaving the solar system just as it had entered it, on a hyperbolic trajectory that would carry it back into interstellar space, into that vast darkness between the stars, where it would tumble for millions more years before perhaps encountering another stellar system, another sun around which to curve, another chance to briefly shine in someone else's sky. The contrast between the two objects, Between the silent, enigmatic Oumuamua and the garrulous green glowing 2I divided by Borisov, raised questions about what constitutes a typical interstellar object, whether there is such a thing as typical when you are sampling from the debris of countless different planetary systems formed under countless different conditions, and most astronomers now believe that both objects are probably representative of different populations, with Oumuamua perhaps being a fragment of a rocky planet or a thoroughly degassed comet nucleus, and 2I divided by Borisov being a more typical comet still rich in volatile ices, and that over time, as we detect more such objects, we will build up a statistical picture that includes many different types. Just as the solar system contains many different types of small bodies, from the icy comets of the Oort cloud to the rocky asteroids of the main belt to the metallic cores of differentiated planetesimals that were shattered in ancient collisions, the distances involved in these objects' journeys are almost impossible to comprehend on any human scale. The nearest star to our Sun, Proxima Centauri, is roughly 4¼ light-years away, which means that light, traveling at 300,000 kilometers per second, takes more than 4 years to make the journey. And an object moving at the speeds typical of interstellar visitors, like Oumuamua or 2I divided by Borisov, would take tens of thousands of years to cover the same distance, and most interstellar objects have probably traveled much farther than this, have crossed tens or hundreds or even thousands of light years during their journey through the galaxy, spending the vast majority of that time in the true depths of interstellar space, where even the nearest stars appear as nothing more than bright points in a black sky, where there is no sun to warm you, no planets to see, just the slow, patient turning of the galaxy and the even slower drift of material through the dark. Try to imagine what that journey must be like from the perspective of the object itself, if an object could have a perspective, tumbling through the void for millions of years, spinning end over end in a complex rotation imparted by whatever event ejected it from its parent system. Perhaps a close gravitational encounter with a giant planet that grabbed it and slung it outward at escape velocity, or perhaps a stellar flyby that disturbed the distant reaches of its planetary system and sent a shower of comets falling inward and outward in all directions. And for eons the object falls through space that is almost perfectly empty, encountering nothing, lit only by the faint collective glow of distant galaxies, its surface slowly altered by cosmic rays, by the occasional impact of an interstellar dust grain, by the slow radioactive decay of elements in its interior, but otherwise unchanging, frozen, patient, until finally it happens to cross the path of another star, happens to fall into the gravitational well of another sun, and suddenly, after all that time in the dark, it is briefly illuminated, briefly warm, briefly observed, before being flung back out into the darkness once more. The human need to find meaning in such objects is itself interesting and perhaps revealing of something fundamental about our psychology. We see a mysterious visitor from beyond our star, and immediately we begin to construct narratives. We wonder if it might be artificial, might be a message, or a probe, or a piece of technology from another civilization. And while such speculation is understandable, and in some sense even scientifically valuable, because it forces us to think carefully about what evidence would actually support such a conclusion, it also reflects our deep desire not to be alone, our longing to find companionship in the universe, to discover that other beings have looked up at their own skies and wondered the same things we wonder, and perhaps developed technologies to reach out across the cosmic distances that separate all thinking beings. The silence of space is not just physical but existential. We have sent radio signals into the cosmos for more than a century now, and we have listened carefully for signals coming back, and we have heard nothing but the hiss of thermal radiation and the occasional burst from a pulsar or the electromagnetic roar of a quasar. But no voice, no message, no evidence that anyone else is out there doing what we are doing, and this silence weighs on the imagination, makes us scrutinize every anomalous object, every unexplained signal, Every datum that does not quite fit our models, looking for the pattern that would tell us we are not alone. And when an object like Oumuamua comes tumbling through our solar system with its strange shape and mysterious acceleration, it is natural, perhaps inevitable, that some of us wonder if this might be that long-sought evidence. That first contact might come not as a radio signal from a distant star, but as a physical object passing through our neighborhood. And even though the evidence for such an interpretation is weak, the desire to find such meaning is strong. And in this tension between evidence and desire, between skepticism and hope, the full complexity of human curiosity reveals itself. Abraham Loeb's advocacy for taking the artificial origin hypothesis seriously became a focal point for debates not just about Oumuamua specifically, but about how science should approach the question of extraterrestrial intelligence more broadly. Whether we should maintain a high degree of skepticism and demand overwhelming evidence before entertaining such possibilities, or whether we should adopt a more open-minded stance and acknowledge that in a universe containing billions of potentially habitable planets, the existence of other technological civilizations is perhaps more likely than not, and that therefore finding evidence of such civilizations should not require extraordinary proof, but rather should be approached with the same standards of evidence we apply to other scientific questions. And this methodological debate is far from settled and likely will continue as long as we lack definitive evidence one way or another. But regardless of whether Oumuamua or any other interstellar object turns out to be artificial, the mere fact that we are now detecting such objects regularly, that we have transitioned from a time when the interstellar nature of small bodies was purely theoretical to a time when we have observed multiple examples and can study their properties empirically, represents a genuine revolution in astronomy, a new window opening onto the galaxy beyond our solar system. And with this window comes new opportunities to learn about planetary systems around other stars, about the chemistry and physics occurring in regions of the galaxy we cannot visit directly, about the diversity of environments in which planets and small bodies form, and about the processes that transport material across the vast distances between stars. The light travel time between stars also has philosophical implications. When we observe Oumuamua or 2I divided by Borisov, we are seeing them as they were at the moment. The light now entering our telescopes left their surfaces, but given their distances from Earth and the finite speed of light, there is always a delay, always a gap between the moment of observation and the moment being observed. And for nearby objects in the solar system, this delay is negligible, seconds or minutes or at most hours. But for interstellar objects that originated from stars light years away, the time it has taken the object to reach us means that when we observe it, we are seeing something that left its parent system millions of years ago, back when the most advanced life on Earth was still microbial, when no eye had yet evolved to look at the stars, when the very concept of observation was still far in the future. And this temporal displacement reminds us that astronomy is always archeology, always the study of the past, always the interpretation of light and other signals that have traveled across space and time to reach us, carrying information about events and conditions that may no longer exist by the time we receive them. The cosmic silence between stars is not just an absence of sound, which cannot propagate through the vacuum of space anyway, but an absence of interaction, an isolation enforced by the sheer scale of the distances involved. Stars are separated from each other by distances millions of times greater than the sizes of the stars themselves, like grains of sand scattered across a continent, and this means that stars almost never interact directly, almost never collide or merge except in the dense cores of globular clusters or during galactic collisions, and most stars live out their entire lives without ever coming close to another star, and the planets orbiting those stars and any beings living on those planets are even more isolated, separated not just by distance but by the limitations of physics, by the speed of light which imposes an absolute upper limit on how fast information can travel, meaning that even if we could send a message to another star, Even if we shouted into the void with the most powerful transmitter we could build, the response would not come back for years or decades or centuries depending on the distance, and this enforced slowness. This cosmic speed limit means that any conversation with another civilization would not be a conversation at all, but rather an exchange of monologues separated by lifetimes. And yet, despite this isolation, despite the silence and the distances and the darkness, matter does flow between stars, slowly, patiently, in the form of objects like Oumuamua and 2I divided by Borisov, and this flow represents a kind of connection, a physical link between stellar systems that would otherwise be completely isolated. And over the billions of years of galactic history, this connection has meant that no star is truly alone, that the material making up every planetary system includes contributions from countless other systems, atoms and molecules that have traveled across light years of space, that have visited many suns before finally settling into orbit around one and condensing into planets or remaining as small bodies in the outer reaches of the system. The orbital mechanics of interstellar visitors are elegantly described by the mathematics of Kepler and Newton, the same equations that govern the motion of planets and moons and asteroids within our solar system, but applied to trajectories that are open rather than closed, hyperbolic rather than elliptical, and the beauty of these equations is that they work equally well. Whether an object is gravitationally bound to the sun or merely passing through, whether it will return in a predictable orbit or will disappear into the void, never to be seen again. Because gravity does not care about the long-term fate of the objects it acts upon, does not distinguish between a temporary visitor and a permanent resident, but simply pulls each body toward each other, body with a force proportional to their masses and inversely proportional to the square of the distance between them. And from this simple law, this elegant mathematical relationship, all the complexity of orbital motion emerges. The escape velocity from the solar system, the speed an object needs to be traveling to break free of the sun's gravity and enter interstellar space, depends on how far the object is from the sun at Earth's distance. It is about 42 kilometers per second, which is why launching interplanetary probes requires such powerful rockets. But farther from the sun, the escape velocity is lower, and in the outer reaches of the solar system where the Oort cloud resides, tens of thousands of astronomical units from the sun, the escape velocity is very low indeed, just tens of meters per second. And this is why gravitational interactions with passing stars or with giant planets in the inner solar system can relatively easily eject Oort cloud objects into interstellar space, whereas ejecting an object from the inner solar system requires much more energy and is correspondingly less common. The trajectories of Oumuamua and 2I divided by Borisov, when plotted in 3 dimensions, are beautiful curves that sweep through the inner solar system, bending around the sun due to its gravitational pull before heading back out in a new direction, like a ball rolling down and then up the sides of a gravitational well. And the degree of bending, the angle through which the trajectory curves, depends on how close the object passes to the sun and how fast it is moving. And for both of these objects, the closest approach to the sun was well inside Earth's orbit, close enough that the sun's gravity significantly altered their trajectories, redirected them by tens of degrees, but not close enough to capture them, not slow enough that they would be pulled into closed elliptical orbits and become permanent members of the solar system. The energy budget of an interstellar object is dominated by its kinetic energy, the energy of its motion through space, which for an object moving at tens of kilometers per second is enormous, even if the object's mass is relatively small. And this energy has to go somewhere when the object enters a planetary system and interacts gravitationally with the star and planets. And what typically happens is that the object exchanges energy with the star, gaining kinetic energy as it falls inward toward the sun and losing it again as it climbs back out, but ending up with the same total energy it started with because gravity is a conservative force, meaning that energy is conserved as long as no other forces act on the object. And this is why Oumuamua's non-gravitational acceleration was so interesting, because it implied that some other force was acting, was adding or removing energy in a way that gravity alone could not account for. The surface temperature of an interstellar object varies dramatically depending on its distance from the nearest star in interstellar space, far from any sun. The only source of heat is the cosmic microwave background radiation, the faint afterglow of the Big Bang that pervades all of space and maintains a temperature of about 2.7 Kelvin, just a few degrees above absolute zero. And this is the temperature that an interstellar object in equilibrium with its environment would approach. Cold enough that even helium would be frozen solid. Cold enough that all chemical reactions essentially stop, that matter exists in a kind of suspended animation, unchanging, waiting, and then when the object enters a stellar system and approaches a sun, its temperature begins to rise, slowly at first as it is still very far away, but then more rapidly as it falls inward. And by the time it passes through the inner solar system, its surface temperature might reach hundreds of degrees Kelvin, warm enough for water ice to sublimate, for frozen gases to vaporize, for the object to awaken from its long frozen sleep and briefly come alive before falling back into the cold dark once more. This thermal cycling, this alternation between frozen quiescence in interstellar space and brief periods of activity when passing near a star, is what shapes the evolution of interstellar comets over their lifetimes. Each time such a comet passes near a star, it loses some of its volatile ices, becomes slightly more inert, and after many such passages, it might become thoroughly devolatilized, transformed into a rocky or carbonaceous body that no longer shows any cometary activity. And perhaps this is what happened to Oumuamua. Perhaps it was once an active comet like 2I divided by Borisov, but has passed near so many stars over its long journey through the galaxy that it has lost all its volatiles and now consists only of refractory materials, silicates and organics that can withstand higher temperatures without sublimating. And this might explain why it showed no obvious cometary activity despite its close approach to the Sun, though this remains speculative and other explanations are certainly possible. The color and reflectivity of interstellar objects provide clues about their composition and history. Oumuamua's reddish color suggested the presence of organic compounds, complex carbon-based molecules that form when simpler ices are irradiated by cosmic rays and ultraviolet light, and these organics accumulate on the surfaces of objects that have spent long periods in interstellar space, forming a kind of reddish crust or mantle that covers whatever pristine material lies beneath. And the fact that Oumuamua was red suggested it had been traveling through space for a very long time, long enough for this organic mantle to develop. Though how long exactly is difficult to say, because the rate at which organics form depends on the intensity of the radiation environment and on the composition of the underlying ices, neither of which we can measure directly for an object we observed only briefly. The reflectivity of Oumuamua, measured by comparing the amount of sunlight it reflected to the amount we would expect based on its distance and size, was relatively low, meaning that it was a dark object, absorbing most of the light that hit it rather than reflecting it. And this is typical of objects covered in organic materials, which tend to be dark, almost black, and this low reflectivity combined with the object's small size made it extremely difficult to detect, and meant that we only saw it because it happened to pass relatively close to Earth, and our telescopes happened to be looking in the right direction at the right time, and many similar objects have probably passed through the solar system undetected, too faint or too fast, or in the wrong part of the sky for anyone to notice. By contrast, 2I divided by Borisov was much easier to study because it was actively shedding gas and dust, creating a large bright coma that made it more visible and more obvious in astronomical images, and the dust in the coma scattered sunlight much more efficiently than the bare nucleus would have, making the comet appear brighter and larger than it actually was. And this is why active comets are generally easier to detect than inert bodies of the same size, why our senses of comets in the solar system is more complete than our senses of asteroids in the same size range, and why we might expect that interstellar visitors that are cometary in nature will be discovered more often than rocky or metallic interstellar asteroids. The question of how many interstellar objects have struck Earth over geological time is fascinating and has implications for theories of panspermia and for our understanding of how Earth acquired its water and organic materials. Calculations based on the density of interstellar objects inferred from the detection rate of Oumuamua and 2I divided by Borisov suggest that Earth should be struck by an interstellar object larger than a meter every few million years on average, and by smaller objects much more frequently. And while most such impacts would be indistinguishable from impacts of solar system objects, they would nevertheless represent a delivery mechanism for material from other stellar systems, a way for molecules and atoms that formed around other stars to become incorporated into Earth's biosphere and geology. If interstellar objects do occasionally collide with Earth, then in principle we might be able to find fragments of them in the geological record, in ancient impact craters, or in layers of sediment that accumulated during periods of heavy bombardment, and one could imagine searching for such fragments by looking for isotopic anomalies or unusual chemical compositions that would mark them as foreign, as visitors from beyond our solar system. Though in practice such a search would be extremely difficult because we would need to distinguish the signature of an interstellar impactor from the much more common signatures of solar system material and terrestrial processes. But perhaps future advances in analytical techniques will make such searches feasible, will allow us to find and study pieces of other stellar systems that have fallen to Earth and been preserved in rock or ice or sediment. The idea that we are being constantly, if rarely, bombarded by material from other stars changes the way we think about Earth's place in the galaxy. We are not an isolated oasis of matter and life floating in an empty void, but rather we are embedded in a vast ecosystem of stellar systems that exchange material slowly over billions of years. And this exchange means that the atoms in our bodies may have visited other stars before they ended up here, may have been part of a comet or asteroid that toured the galaxy before finally falling to Earth and being incorporated into living organisms. And while the fraction of Earth's material that has such an exotic origin is probably very small, it is not zero. And this is a kind of connection, a physical link to the rest of the galaxy that exists, regardless of whether there is life elsewhere or whether anyone is listening to our radio signals. The rotation rates of Oumuamua and 2I divided by Borisov differed significantly. Oumuamua tumbled chaotically, with a period of about 8 hours, meaning that it completed one full rotation every 8 hours, though the rotation was complex enough that talking about a single period is somewhat misleading, whereas 2I divided by Borisov rotated more sedately, and the difference in rotation behavior might reflect differences in their shapes, their internal structures, their histories of collisions and close encounters with planets, all of which can impart angular momentum and change how an object spins. And for objects that tumble chaotically like Oumuamua, the rotational state can evolve over time as energy is dissipated through internal friction, gradually damping out the more complex modes of rotation and leaving only the simplest spin around a single axis. Though this process can take millions of years and may not have had time to fully operate on Oumuamua if it was ejected from its parent system relatively recently. The public reaction to these interstellar visitors was a mixture of fascination, wonder, and in some cases disappointment that they were not more obviously alien, not more dramatic in their appearance or behavior. People imagined sleek probes bristling with antennas or vast generation ships carrying colonies of extraterrestrial beings, and what they got instead were dim points of light in telescopic images, objects that required careful analysis to distinguish from ordinary asteroids and comets. And while this might seem anticlimactic, it is actually deeply appropriate because the universe is not obligated to provide us with drama or spectacle, is not organized according to human narrative conventions, and sometimes the most profound discoveries are quiet ones, subtle departures from expectation that only become meaningful when you understand the context, when you appreciate how strange it is that anything at all should be visiting from beyond our star. The naming conventions for interstellar objects are still being worked out by the International Astronomical Union, the body responsible for assigning official designations to celestial objects. When Oumuamua was discovered, there was no established procedure for naming interstellar visitors because none had been discovered before, and so the normal rules for comets and asteroids were adapted, and the object was given the designation 1I divided by 2017 U1, indicating that it was the first interstellar object discovered and that it was first observed in the year 2017 during the second half of October, and then it was given the name Oumuamua in recognition of its Hawaiian discovery site, and similarly 2I divided by Borisov was designated as the second interstellar object and named for its discoverer, and presumably future interstellar objects will be numbered sequentially as 3I, 4I, 5I, and so on, and this naming system reflects the expectation that such discoveries will become routine, that we are entering an era where detecting visitors from beyond our solar system is no longer extraordinary, but is simply part of the ongoing survey of the sky. The sensitivity of modern telescopes and sky surveys has increased dramatically over the past few decades, to the point where objects that would have been completely undetectable a generation ago are now routinely discovered and tracked, and this increase in sensitivity is what has made the detection of interstellar objects possible, because these objects are typically very faint, much fainter than the planets and brighter asteroids that dominate the appearance of the sky. And it is only through systematic automated surveys that scan the entire sky repeatedly, taking thousands of images every night and processing them with sophisticated software to identify anything that moves or changes, that we can hope to catch these fleeting visitors during their brief passage through our neighborhood. The future of interstellar object studies looks bright, or perhaps it would be more accurate to say it looks faint but increasingly detectable. Because as new telescopes come online and as survey capabilities continue to improve, we can expect the discovery rate of interstellar objects to increase, perhaps dramatically. The Vera Rubin Observatory, currently under construction in Chile, will conduct a survey called the Legacy Survey of Space and Time that will image the entire visible sky every few nights with unprecedented depth and sensitivity, and simulations suggest that this survey might detect dozens or even hundreds of interstellar objects per year once it reaches full operation, transforming our understanding of these visitors from the realm of rare anomalies to a well-characterized population with measurable statistical properties. With larger samples of interstellar objects, we will be able to answer questions that are currently unanswerable. We will be able to determine what fraction are cometary versus asteroidal in nature, whether the size distribution of interstellar objects matches what we see in the solar system or is different in ways that reflect different formation environments, whether there are any truly bizarre objects that do not fit into existing categories and might require new explanations, and whether the chemical compositions of interstellar comets cluster around certain values suggesting common formation conditions or are widely scattered, suggesting great diversity among planetary systems. The possibility of sending a mission to intercept an interstellar object is tantalizing but challenging. Oumuamua was moving so fast and was discovered so late after it had already passed closest approach to the Sun and was heading back out, that no existing rocket could have caught it. But if we had detected it earlier, months or years before it entered the inner solar system, a mission might have been feasible. And going forward, there are proposals for rapid response spacecraft that could be kept in a state of readiness and launched on short notice when an interesting interstellar object is detected. Spacecraft that would carry cameras and spectrometers and perhaps even sampling equipment to collect material directly from the object's surface or coma, and such a mission would be extraordinarily valuable scientifically, because it would allow direct analysis of material from another stellar system, would give us ground truth about the composition and structure of interstellar visitors that we can currently only infer from remote observations. The engineering challenges of such a mission would be considerable. The spacecraft would need to be capable of accelerating to very high velocities in a short time, would need to navigate precisely to intercept a small, fast-moving target, and would need to carry sufficient fuel or use gravity assists from planets to match velocities with the object so that the encounter time could be extended from a few seconds to minutes or hours or even longer, allowing detailed observations and measurements. And all of this would need to be done within the tight time constraints imposed by the fact that interstellar objects spend only a few months or at most a year within the inner solar system, where spacecraft can reach them before recede into the distance and become too far away to pursue. But despite these challenges, several mission concepts have been proposed and are being studied by space agencies, including NASA's Interstellar Object Explorer and ESA's Comet Interceptor. And while these missions are still in the planning stages and face significant funding and technical hurdles, the mere fact that they are being seriously discussed shows how far we have come in recognizing interstellar objects as legitimate and important targets for exploration, not just as curiosities to be observed from afar, but as destinations worthy of dedicated spacecraft, as bridges to other stellar systems that we can study in detail to learn about the galaxy beyond our immediate neighborhood. The philosophical implications of interstellar visitors extend beyond questions of whether they might be artificial and into deeper territory about the nature of cosmic exploration and discovery. Every object that arrives from beyond our solar system is a time capsule, carrying information about conditions in its parent system billions of years ago. Because that is when it formed, when the elements and molecules that compose it were still part of a protoplanetary disk orbiting a young star, and the chemistry and isotopic ratios preserved in the object reflect the conditions in that disk, the temperature and pressure and elemental abundances that prevailed. And by studying these visitors, we are engaging in a kind of paleontology, reconstructing the history of environments we will never visit, learning about the diversity of outcomes that are possible when interstellar clouds collapse and form stars and planets. The loneliness of these objects is profound when you think about it. Cast out from their parent systems by gravitational interactions, they wander the galaxy alone, never to return to the place where they formed, never to orbit a star again, except briefly and at a distance, during rare passages like the ones that brought them to our attention. And they spend the vast majority of their existence in the cold dark between stars, in regions where the density of matter is so low that a cubic kilometer of space might contain only a few atoms, where the closest thing to company is the occasional interstellar dust grain drifting past at relative velocities of tens of kilometers per second. And yet, despite this isolation, they carry within them a connection to their origins, a chemical memory of the place and time of their birth that persists across millions of years and light years of travel. The fact that two interstellar objects were detected within just 2 years of each other after decades of searching and speculation might seem like an improbable coincidence, but it likely reflects the improving capabilities of sky surveys more than any clustering in the arrival times of such objects. Pan-STARRS became fully operational in 2010 and has since discovered thousands of asteroids and comets. And its sensitivity and cadence are sufficient to detect interstellar objects if they happen to pass through the portion of sky it monitors. And ATLAS, which discovered 2I divided by Borisov, began operations in 2015 and complements Pan-STARRS by scanning the sky more frequently though with less depth, and together these surveys and others like them have created a detection network that makes it very likely we will spot interstellar objects when they visit. Whereas before these surveys came online, such objects would have passed through unnoticed unless they happened to be very bright or to pass very close to Earth. The word interstellar itself carries a weight of meaning and implication. It denotes the space between stars, that vast ocean of near emptiness that separates stellar systems. And to say that an object is interstellar is to say that it has crossed that ocean, has survived the journey through conditions that are hostile to most forms of matter, that it has persisted across timescales that dwarf human history, that it is in some sense a survivor, though of course the object itself has no awareness of survival, or of journey, or of any of the meanings we project onto it, but simply exists and moves according to the laws of physics, indifferent to whether anyone observes it or assigns it significance. The debate over Oumuamua's nature, whether it is a comet, an asteroid, a fragment of a planet, or something more exotic, illustrates how difficult it can be to categorize objects that fall outside our experience, that do not quite match the templates we have developed based on studying objects in our own solar system. And this difficulty is a reminder that the categories we use to organize our understanding of the universe are human constructs, tools for thinking rather than fundamental features of reality, and sometimes reality presents us with things that do not fit neatly into our categories, that require us to expand or modify our classification schemes, or perhaps to accept that not everything can be cleanly categorized, that there is a continuum of properties rather than discrete types. The green glow of ʻOumuamua divided by Borisov, beautiful and eerie in photographs, is a reminder that the universe is full of colour, that different chemical processes produce different hues, and that by analysing these colours we can learn about the invisible processes occurring in and around astronomical objects. The green comes from diatomic carbon, but comets also produce other colours, red from sodium, blue from ionized carbon monoxide, and these colours appear in different intensities depending on the comet's composition and activity level, creating a kind of cosmic rainbow that would be spectacular to see in person, though, of course, in person means from a spacecraft, because no human will witness a comet's coma from close range in the foreseeable future. At least not without being inside a very sophisticated vehicle designed to protect against the vacuum and cold and radiation of space. The trajectories of both Oumuamua and ʻOumuamua divided by Borisov are now taking them beyond the solar system, back into interstellar space, and we can calculate where they will be thousands of years from now, millions of years from now, can predict their paths through the galaxy with reasonable accuracy, as long as we account for the gravitational influence of all the stars and the dark matter they will pass near, though over very long timescales the precision of such predictions decreases, because small uncertainties accumulate, and because the galaxy itself is not static, but is constantly evolving, with stars moving and interacting, and occasionally exploding, redistributing matter and energy. And all of this affects the trajectories of small objects drifting through the void, makes their long-term fates uncertain even though their immediate futures are calculable. Neither Oumuamua nor ʻOumuamua divided by Borisov will ever return to our solar system. Their velocities relative to the Sun are high enough that even accounting for the Sun's gravity, they will escape into interstellar space permanently, will never be turned around and brought back. And so the brief observations we made during their passage through our neighbourhood are all we will ever have, are all the data we will ever collect on these specific objects, unless by some extraordinary chance a future spacefaring civilization encounters one of them again in some distant part of the galaxy millions of years from now, and things as it is the same object that once passed through our solar system, though of course there would be no way to know this without some kind of marker or signature that identified it, and we placed no such marker, had no opportunity to do so, even if we had wanted to, because we discovered these objects too late and could not reach them in time. The scientific papers written about Oumuamua and ʻOumuamua divided by Borisov number in the hundreds now, covering every aspect of their detection, characterization, orbit determination, physical properties, and theoretical interpretation, and this flood of papers reflects both the object's intrinsic interest and the fact that they represent a new class of phenomena about which much can be said and little can be definitively proven, creating a kind of scholarly playground where ideas can be proposed and debated without the constraints that apply when studying better characterized objects. And while some of these papers will prove prescient and others will be forgotten as more data accumulates, collectively they represent a snapshot of a scientific community grappling with something genuinely new, trying to integrate unexpected observations into existing frameworks and occasionally suggesting that new frameworks might be needed. The impact velocity of an interstellar object colliding with Earth would be extremely high, higher than typical solar system impactors, because the object would be moving at its interstellar velocity plus whatever additional speed it gained, falling into Earth's gravity well. and the kinetic energy of such a collision scales with the square of the velocity, meaning that a relatively small interstellar object could release as much energy as a much larger solar system object moving more slowly, and this has implications for the cratering and damage such impacts would cause, though it should be emphasized that collisions between Earth and interstellar objects are very rare, probably occurring only once every few million years for objects large enough to survive passage through the atmosphere, and so they do not represent a significant hazard to civilization, are merely an interesting footnote to the broader story of Earth's bombardment history. The atoms and molecules that make up interstellar objects have their own histories, their own journeys that began in the hearts of stars, where they were forged through nuclear fusion, where lighter elements were combined into heavier ones in the tremendous heat and pressure of stellar interiors, and then were ejected into space when those stars died, either gently through stellar winds for stars like the Sun, or violently through supernovae for more massive stars, and these atoms drifted through interstellar space, mixing with gas and dust in giant molecular clouds, until eventually they condensed into new stars and planets, and some fraction ended up in the objects we now call Oumuamua and 2I divided by Borisov, and these objects carry that stellar heritage with them, are made of star stuff just as we are, just as everything in the universe is except for the hydrogen and helium that were created in the Big Bang itself. The temperature of space far from any star is not absolute zero, but is instead the temperature of the cosmic microwave background, roughly 2.7 Kelvin, and this temperature is a relic of the Big Bang, the remnant heat from when the universe was young and hot, and filled with a glowing plasma. And over the billions of years since then, the universe has expanded and cooled, and that glow has redshifted into the microwave part of the spectrum, invisible to the human eye, but detectable with radio telescopes, and this faint radiation pervades all of space, means that no object is ever truly isolated, that everything in the universe is constantly bathed in this weak but universal glow, and for an interstellar object drifting far from any star, this cosmic microwave background is the only source of external heat, though it is so weak that it barely affects the object's temperature at all, and the object simply cools down to equilibrium with this radiation and remains at that temperature more or less indefinitely. The discovery images of both objects are unimpressive to untrained eyes, just dots on a background of other dots. But to astronomers they are treasure, data that can be analysed and reanalyzed to extract every possible piece of information, positions measured to fractions of a pixel, brightnesses compared between different filters to determine colours, motions tracked across multiple images to determine trajectories, and from these simple measurements, an entire picture emerges, a story of an object's origin and journey and physical properties, and this is the power of modern astronomy. The ability to learn so much from so little, to reconstruct the biography of an object from nothing but the light it reflects or emits. The possibility that some interstellar objects might be fragments of exoplanets, pieces of rocky worlds that were shattered in collisions and ejected from their parent systems, is intriguing because it suggests that, by studying such objects, we might be able to learn about the composition and structure of exoplanets directly, something that is currently very difficult to do because most exoplanets are detected only through indirect methods like transits or radial velocity variations, and we have no way to sample their surfaces or interiors. But if we could identify an interstellar object as being a planetary fragment and could study its composition in detail, either through spectroscopy or ideally through a sample return mission, we would gain invaluable information about planetary formation and differentiation processes in other stellar systems. The orbital dynamics of interstellar objects as they pass through the solar system are influenced by all the major planets, but especially by Jupiter, which is so massive that its gravitational influence extends throughout the solar system, and many interstellar objects will pass relatively close to Jupiter during their transit through our neighborhood, and when they do, Jupiter's gravity can significantly alter their trajectories, bending them, speeding them up, or slowing them down. And in some cases, Jupiter's gravity could even capture an interstellar object, transforming its hyperbolic trajectory into an elliptical one and making it a permanent member of the solar system. Though this is unlikely, because the object would need to lose a very precise amount of energy at just the right moment. But it is not impossible. And some astronomers have speculated that a few of the objects we think of as native to the solar system, particularly some of the Jupiter Trojans or other unusual asteroids, might actually be captured interstellar objects that were adopted by the solar system long ago. The distinction between an interstellar object and a solar system object is fundamentally about energy. An object is gravitationally bound to the Sun if its total energy, kinetic plus potential, is negative, meaning that the object does not have enough velocity to escape the Sun's gravity and will therefore remain in the solar system forever, or at least until something perturbs its orbit. And an object is unbound if its total energy is positive, meaning it has more than enough velocity to escape and will therefore leave the solar system on a hyperbolic trajectory. And measuring whether an object is bound or unbound requires precise determination of its position and velocity, which in turn requires multiple observations over an extended period. And for both Oumuamua and 2I divided by Borisov, these observations clearly showed positive total energy, unambiguously marking them as interstellar visitors rather than solar system natives. The excitement in the astronomical community when each object was confirmed as interstellar was palpable, expressed in press releases and social media posts and conference presentations, because these were historic discoveries. The first time humanity had identified objects from beyond our solar system passing through our neighborhood, and there was a sense of a new era beginning. An era in which such discoveries would become routine, in which we would transition from speculating about interstellar visitors to studying them empirically. And this sense of excitement was tempered by frustration that the objects could not be studied in more detail, that they were already receding by the time we recognized them for what they were. But overall, the mood was one of anticipation, of looking forward to future discoveries and to the insights they would bring. The colors of objects in space reveal their chemistries and their histories. Red objects tend to be organic rich, their surfaces covered in complex carbon compounds that have been irradiated over long periods, while grey objects are more rocky, composed of silicates and metals, and very dark objects may be carbonaceous, rich in primitive materials that have not been significantly heated or processed since they formed in the early solar system or in the early history of their parent system. And by measuring colors precisely, by comparing the amount of light an object reflects at different wavelengths, astronomers can infer what materials are present on its surface, though this inference is indirect and model-dependent, and there is often ambiguity, multiple compositions that could produce similar colors. And so, color alone is not enough to uniquely determine composition, but must be combined with other information like spectroscopy or radar observations, or direct sampling when possible. The thought that billions of interstellar objects are drifting through the Milky Way at any given moment, most of them never coming close enough to any star to be illuminated or observed, is both humbling and strangely comforting. Humbling, because it reminds us how much of the universe exists beyond our perception, how much is happening that we will never see or know about, and comforting because it suggests that the galaxy is not as empty as it sometimes seems, that there is connection and exchange happening constantly, that matter and information flow through the cosmos in ways we are only beginning to understand, and that we are participants in this flow whether we know it or not, receiving visitors from distant systems and sending our own debris out into the galaxy to potentially be detected by other civilizations in the distant future. The velocity distribution of stars in the galaxy is well characterized. Most stars near the Sun are moving at roughly 20 to 30 kilometers per second relative to the local standard of rest, with some moving faster and some slower, and this distribution reflects the fact that stars formed at different times and places in the galaxy and have been perturbed by various gravitational interactions over their lifetimes, and the velocity distribution of interstellar objects should be similar to that of stars. because the objects were ejected from planetary systems around those stars and initially shared their velocities. Though the ejection process itself can add or subtract velocity, and indeed both Oumuamua and 2I divided by Borisov had velocities consistent with being typical members of the local population of stars, neither unusually fast nor unusually slow, which is what one would expect if they were ejected from planetary systems in our general neighborhood of the galaxy. The question of whether we will ever be able to trace an interstellar object back to its parent star is difficult. The problem is that both the object and the star are moving, and they have been moving for millions of years, and the galaxy is full of stars moving in different directions at different speeds. And tracing these motions backward through time becomes increasingly uncertain as errors and perturbations accumulate. And so for old interstellar objects that have been traveling for many millions of years, the parent star is probably impossible to identify with certainty. There are simply too many candidates and too much uncertainty. But for young interstellar objects, ones that were ejected relatively recently, it might be possible, with very precise measurements of the object's trajectory and good models of stellar motions, to narrow down the list of candidate parent stars to a few possibilities, though even then a unique identification would be challenging. The albedo of an object, the fraction of incident sunlight that it reflects, is a key parameter for understanding its surface properties. Bright objects with high albedo are typically icy or covered in fresh frost, while dark objects with low albedo are rocky or carbonaceous or covered in organic materials, and albedo affects how much sunlight an object absorbs and therefore how warm it gets when near the sun. And this in turn affects whether ices will sublimate and whether the object will display cometary activity. And so albedo is one of the pieces of information astronomers try to determine for any new object, though measuring it requires knowing the object's size, which is often difficult to determine without direct imaging. And so there is usually uncertainty, and multiple parameters have to be fit simultaneously from the available data. The mass of an interstellar object is almost impossible to determine from remote observations alone, unless the object happens to have a moon or makes a very close approach to a planet whose orbit is perturbed measurably. And without knowing the mass, we cannot calculate the object's density. And without knowing the density, we have limited ability to determine whether the object is primarily rocky, icy, or metallic. And so one of the most basic properties of these visitors remains unknown, can only be estimated based on assumptions about what typical asteroids or comets in the solar system are like, and extrapolating that to the interstellar case. And these estimates might be correct, but they might also be significantly wrong if interstellar objects have different properties than solar system objects on average. The moment of closest approach to the Sun is called perihelion, and for both Oumuamua and 2I divided by Borisov, this occurred at distances well inside Earth's orbit, close enough that the Sun's heat would have been intense, close enough that any volatile ices would have been strongly heated and would sublimate rapidly if present on the surface, and for 2I divided by Borisov. This heating drove vigorous cometary activity, produced the coma and tail that made it easy to detect and study, while for Oumuamua the same heating produced little obvious effect, no visible coma or tail, though there was that mysterious non-gravitational acceleration that suggested something was outgassing even if it was not visible. And the different responses of these two objects to similar heating underscores their different natures, their different compositions or structures or histories. The hyperbolic trajectory of an interstellar object means that it approaches the Sun from a particular direction, swings around it, and then heads off in a different direction. And the angle between the incoming and outgoing directions depends on how close the object passes to the Sun and how fast it is moving. And this angle can range from almost 180 degrees for an object that barely bends around the Sun to much smaller angles for objects that pass very close or are moving very slowly. And both Oumuamua and 2I divided by Borisov had moderate bending angles, tens of degrees, enough to significantly redirect their trajectories, but not enough to turn them around completely. And so they are now heading toward different parts of the galaxy than they came from, and over millions of years, this effect will carry them to different regions of the Milky Way than they would have reached if they had never encountered our solar system. The amount of time each object spent within the orbit of Neptune, the outermost major planet in the solar system, was just a few months, a brief visit by cosmic standards, but long enough for multiple telescopes to observe them, for data to be collected, for scientists to analyze and debate their properties, and then they were gone, receding into the distance at speeds that telescopes cannot match, becoming fainter and fainter until they dropped below the detection threshold and could no longer be tracked. And now they are once again interstellar objects, once again travelers in the dark, invisible to us, unknowable except for the brief record of observations we made during their fleeting passage through our neighborhood. The concept of a battle between Oumuamua and 2I divided by Atlas is of course metaphorical. These objects are not in competition, are not aware of each other or of us, are simply following the dictates of gravity and momentum through space. But the metaphor captures something of the way they have competed for public attention, for scientific resources, for the imagination of people trying to understand what it means that these visitors have come. And in the public discourse there has been a kind of contest between them, with Oumuamua's mystery and potential exoticism pitted against 2I divided by Borisov's familiarity and activity, and different people have found different aspects of this contrast appealing, some preferring the enigmatic puzzle of Oumuamua, and others appreciating the more straightforward beauty of 2I divided by Borisov. But ultimately both objects are valuable, both are teaching us things we did not know before, both are expanding our understanding of the galaxy and our place in it. And the fact that they are so different from each other is itself informative, tells us that interstellar space contains a diversity of objects with different origins and histories and properties, and that by studying many such objects over time, we will build up a picture of what is typical and what is rare, of what processes dominate the formation and evolution of small bodies and planetary systems throughout the galaxy, and of how material flows through the cosmos over billions of years, connecting stars and systems that seem isolated, but are in fact all part of a single galactic ecology. The legacy of the first two interstellar visitors will extend far beyond their brief moments of observation. They have opened a new field of study, interstellar object astronomy, and have inspired new mission concepts, new telescope designs, new analytical techniques, and new theoretical models. And they have captured public imagination in a way that few astronomical discoveries do, have reminded people that we live in a universe full of wonders, that there are still frontiers to explore and mysteries to solve, that the cosmos is not a static backdrop, but a dynamic system full of motion and change and connection, and that sometimes the messengers from distant places arrive not with fanfare but quietly, as faint points of light moving against the stars, requiring patience and skill to detect, but rewarding those who do with glimpses of worlds we will never visit. The fact that both objects were discovered from Earth-based telescopes rather than from space-based observatories is worth noting. While space telescopes like Hubble have many advantages, particularly for detailed follow-up observations, the initial detection of fast-moving objects like interstellar visitors benefits from the large field of view and frequent cadence that ground-based surveys can provide, and the success of Pan-STARRS and Atlas in finding these objects demonstrates that ground-based astronomy remains vital and that the next generation of ground-based telescopes will likely discover many more such visitors, and space-based telescopes will continue to play a complementary role in characterizing them once they have been found. The chemistry of comets is a window into the conditions in protoplanetary disks, those swirling clouds of gas and dust that surround young stars and from which planets eventually form, because comets preserve in their ices a record of the molecules that were present in the outer regions of those disks, regions cold enough that even volatile substances could freeze and be incorporated into solid bodies, And by measuring the relative abundances of different molecules in cometary ices, we can infer the temperature and density and chemical environment in the protoplanetary disk. And comparing these abundances between solar system comets and interstellar comets, like 2I divided by Borisov, tells us how much variation exists between different planetary systems, how universal the conditions were that produced our solar system, versus how much they varied from place to place. The unusual carbon chemistry of 2I divided by Borisov, particularly its high carbon monoxide content, suggests it formed in a region of its parent protoplanetary disk that was very cold, perhaps colder than the regions where most solar system comets formed, or that the disk itself had a different composition, perhaps because the molecular cloud from which it collapsed had different elemental abundances due to its location in the galaxy or its enrichment history from previous generations of stars, and these subtle differences in formation conditions propagate through the entire process of planetary system formation and evolution, affecting what kinds of planets form, where they form, what their atmospheres are like, and ultimately, whether they can support life. And so understanding the diversity of chemical compositions in interstellar comets is relevant to the broader question of habitability throughout the galaxy. The parallax method, which astronomers use to measure distances to nearby stars by observing how they shift position against more distant background objects as Earth orbits the Sun, cannot be applied to interstellar objects in the same way because the objects themselves are moving too fast, but the principle is related by observing an interstellar object from multiple locations or at multiple times. We can triangulate its position and trajectory more precisely, and this is essentially what is done when multiple observatories around the world observe the same object, each from a slightly different vantage point. And the data from all these observations are combined to solve for the object's orbit with higher accuracy than any single observatory could achieve alone. The probability that an interstellar object will collide with the Sun is actually quite low despite the Sun's large size, because space is so vast and the Sun occupies such a tiny fraction of it. And most interstellar objects that pass through the solar system pass well outside the Sun's physical radius. And those that do pass very close to the Sun, close enough to graze its surface or dive into it, would be heated to extremely high temperatures and would likely be completely destroyed, vaporized by the intense heat, and detecting such a collision would be challenging unless we happen to be monitoring the Sun with the right instruments at the right time. And it is possible that such collisions occur occasionally, but have simply not been observed yet. The question of what we would do if we detected an interstellar, our object on a collision course with Earth, is interesting to contemplate. The answer depends on many factors, including how large the object is, how much warning we have, what technologies are available for deflecting asteroids, and whether the object is more like Oumuamua or more like 2I divided by Borisov, because strategies for dealing with a solid rocky body are different from strategies for dealing with a comet full of volatile ices, and fortunately such a collision is extremely unlikely. The probability is vanishingly small given the size of Earth compared to the vastness of space, but if it did happen, it would be a significant event both scientifically and practically. And presumably there would be international efforts to study the object in detail before it struck and to deflect it if possible. The names we give to things matter, shape how we think about them, and the choice to use Hawaiian names for interstellar objects discovered by pan-stars reflects both the location of the telescope and a desire to honor the indigenous culture of Hawaii, and Oumuamua in particular has a poetic resonance. The idea of a scout or messenger, the one who reaches out first from a distant place, and this name has stuck in the public imagination in a way that a purely technical designation like 1I divided by 2017 U1 never could have. And this shows the importance of good naming conventions in making science accessible and meaningful to people beyond the scientific community. The silence of these objects, their lack of any signal or message or obvious artificiality, is itself meaningful, tells us that if there are civilizations out there building probes or spacecraft or megastructures, they are either very rare, or they are not sending them through our neighborhood, or they are using designs and materials that look indistinguishable from natural objects to our current instruments. And this non-detection is consistent with the broader pattern in the search for extraterrestrial intelligence, where decades of listening have produced no confirmed signals, no evidence of technological activity, just silence. And this silence is one of the great puzzles of our time, the Fermi paradox. The question of why the galaxy appears to be empty of other civilizations, when the numbers suggest there should be many, and interstellar objects like Oumuamua, with their tantalizing hints of strangeness, are part of this puzzle, even if they ultimately prove to be entirely natural. The brightness variations of Oumuamua as it tumbled revealed not just that it was elongated, but provided clues about its surface properties. If the surface were perfectly smooth and uniformly reflective, the brightness variations follow a simple mathematical pattern. But the actual variations were more complex, suggesting either that the shape was more irregular than a simple cylinder or cigar, or that the surface reflectivity varied across the object, with some areas brighter than others, perhaps due to patches of different composition or different degrees of weathering. And these subtleties in the light curve are part of what made characterizing Oumuamua so challenging, because the data could be fit by multiple different models, and it was difficult to determine which model was correct without additional information. The concept of stellar systems as archipelagos in a vast ocean of space is apt. Each star is an island of light and warmth in the cold darkness, surrounded by its planets and asteroids and comets. And between these islands, the space is not empty, but is sparsely populated with drifters, objects that have left one island and are slowly making their way toward others. And some of these drifters will eventually be captured by another island, will join a new stellar system, while others will wander forever. And this image of archipelagos connected by drifting debris helps us visualize the structure of the galaxy, helps us understand that nothing is truly isolated, that there are connections even across the vast distances between stars. The rotation states of small bodies are influenced by a phenomenon called the Yorp effect, which stands for Yarkovsky-O'Keefe-Radzievsky-Paddock, named after the scientists who worked out the theory. And the effect arises because irregular bodies absorb sunlight on their sunlit sides and re-radiate that energy as heat. And because the body is rotating, the re-radiation happens from different parts of the surface at different times, and this creates a tiny torque that can speed up or slow down the rotation over millions of years. And for objects in the solar system, this effect has been measured and is significant, and it would operate on interstellar objects as well during their brief passages near stars, though whether it has time to significantly change their rotation states during a single passage is questionable. The possibility of future archaeological missions to study interstellar objects that collided with Earth or the Moon in the past is fascinating. If large interstellar objects struck the Moon, for instance, they might have created impact craters that could be visited and studied, and the impactor material might still be present mixed with the lunar regolith. And by searching for isotopic anomalies or unusual chemical signatures, we might be able to identify impact sites that represent interstellar collisions versus the much more common impacts of solar system objects. And this would give us samples of material from other stellar systems that we could analyze in detail in laboratories, something that would be extraordinarily valuable scientifically, even if the samples were heavily processed by the impact and difficult to interpret. The time it takes light to travel between stars is substantial. Light from the nearest star, Proxima Centauri, takes 4.24 years to reach us, which means that when we observe that star, we are seeing it as it was 4.24 years ago. And for more distant stars, the lag is correspondingly greater, and this means that in a very real sense, astronomy is the study of history. We are always looking into the past, and an interstellar object that originated from a star 10 light-years away carries with it information about conditions in that stellar system from millions of years ago, which is when the object was likely ejected. And so these visitors are time capsules in both a figurative and a literal sense, carrying information from distant places and distant times. And by studying them, we are engaging in a kind of cosmic archeology. The question of what happens to interstellar objects over extremely long timescales, billions of years, is interesting. Do they eventually collide with stars or planets or other objects and get destroyed? Or do they continue wandering forever? And the answer is probably a bit of both. Some fraction will eventually collide and be destroyed, while others will continue drifting. But over billions of years, even in the sparse environment of interstellar space, collisions with dust grains and erosion by cosmic rays will slowly wear away the surfaces of these objects, will ablate material atom by atom, and eventually even a large object might be worn down to nothing, though this process is extremely slow, and most interstellar objects probably survive more or less intact for the entire age of the galaxy. The community of astronomers who study small bodies in the solar system, asteroids and comets and meteoroids, had to adapt quickly when interstellar objects began to be detected. They had to develop new techniques and new ways of thinking about objects that did not fit neatly into the existing frameworks. And this adaptation has been largely successful, has led to new insights and new questions, and has enriched the field considerably. And going forward, the study of interstellar objects will probably become a standard part of planetary science and astronomy, no longer a novelty, but a routine aspect of understanding the solar system and its place in the galaxy. The media coverage of both Oumuamua and 2I divided by Borisov was extensive, with articles appearing in newspapers and magazines and websites around the world, and much of the coverage focused on the question of whether the objects might be artificial, might be probes from another civilization. And while this focus was understandable given the public interest in extraterrestrial life, it sometimes overshadowed the more subtle but equally fascinating scientific story about what these objects could teach us about planetary system formation and galactic ecology. And scientists found themselves in the difficult position of trying to communicate the genuine excitement of the discoveries, while also tempering speculation and emphasizing what was actually known versus what was merely possible. The velocity of Oumuamua relative to the local standard of rest was actually quite modest, just a few kilometers per second, which means that it was moving roughly with the average motion of stars in our neighborhood of the galaxy. And this suggests it may have been ejected from a planetary system relatively nearby, perhaps within a few tens of light years, though identifying the specific system is impossible with current data. And the same is true for 2I divided by Borisov, whose velocity was also typical of the local stellar population. And this is actually reassuring because it means that the objects we are detecting are representative of the local environment, rather than being unusual high-velocity visitors from exotic parts of the galaxy. The tidal forces experienced by an interstellar object as it passes close to the Sun are generally not strong enough to disrupt a solid body unless the object passes extremely close, within a few solar radii. But for a loosely bound rubble pile or a comet with low tensile strength, the forces during a close passage could be sufficient to cause structural damage or fragmentation, and the fact that 2I divided by Borisov did fragment during its passage through the solar system might indicate that it was not a monolithic block, but rather a more fragile aggregate of smaller pieces held together loosely by gravity and ice. And understanding the internal structure of these objects is important for assessing their hazard potential and for planning any future missions that might attempt to land on or sample them. The idea that we are living through a special time, the first few years when interstellar objects are being detected and characterized, is both true and misleading. It is true in the sense that we are indeed among the first humans to observe and study such objects, to know for certain that visitors from other stellar systems pass through our neighborhood, but it is misleading in the sense that this has always been happening, has been happening for billions of years, and we are simply now developing the tools to detect it, to see what has always been there, but was invisible to us. And in this sense, we are not living through something new, but rather are finally becoming aware of something old. something that has been part of the galaxy's natural processes since stars first began forming planets. The brightness of an interstellar object depends on its size, its albedo, its distance from the Sun, and its distance from Earth, and all of these factors work together to determine whether the object is detectable with current telescopes or is too faint to see. And for most interstellar objects that pass through the solar system, the answer is that they are too faint. They pass undetected because they are small or distant or dark or all three, and only a tiny fraction happen to be large enough or close enough or reflective enough to be spotted. And this means that for every interstellar object we do detect, there are probably hundreds or thousands that we miss, and the population we can observe is biased toward larger, brighter objects that pass relatively close to Earth, and extrapolating from this biased sample to the true population requires careful statistical modeling. The way that sunlight reflects off an object's surface depends on the texture and composition of that surface. A smooth, icy surface will reflect light specularly, like a mirror, producing bright reflections from certain angles, while a rough, rocky surface will scatter light diffusely in all directions, appearing more uniformly bright but less intensely so, and by measuring how an object's brightness changes with viewing angle, the geometry of sun-object observer, astronomers can infer properties of the surface, though this requires observations from multiple angles, which for fast-moving interstellar objects is often not possible, and so there is usually significant uncertainty about surface properties. Reader. Long-term fate of the material that makes up Oumuamua and 2I divided by Borisov is an interesting question. Will these objects continue wandering the galaxy forever, or will they eventually be destroyed? And if so, how will they collide with a star or planet? Will they fall into a black hole? Will they be eroded away by interstellar dust impacts and cosmic rays over billions of years? Or will they survive indefinitely? And the answer probably depends on the specifics of their trajectories and on random chance. But over the lifetime of the galaxy, tens of billions of years, the probability that any given small object will be destroyed approaches certainty, though the timescale for this destruction is so long that for all practical purposes we can think of these objects as effectively immortal, at least on human timescales. The seasonal variations in Earth's sky survey coverage mean that some parts of the sky are observed more frequently and more thoroughly than others, and this creates detection biases. Interstellar objects that pass through well-observed regions are more likely to be detected than those that pass through poorly observed regions. And this means that the sample of interstellar objects we have discovered is not necessarily representative of the full population, is biased in ways that need to be accounted for when making statistical inferences, and future all-sky surveys that provide more uniform coverage will help to reduce these biases and give us a more accurate picture of the interstellar object population. The emotional resonance of these discoveries extends beyond the scientific community. People around the world have found themselves moved by the idea that something from another solar system has visited ours, have felt a sense of connection to the broader galaxy, have been reminded of the vastness of the cosmos and our small place within it, and have experienced wonder and curiosity, and perhaps a renewed sense of how much we have yet to learn. And these emotional responses are part of what makes these discoveries valuable, not just as scientific data, but as cultural moments that help us contextualize our existence and our relationship with the universe. The spectroscopy of 2I divided by Borisov, analyzing the light that passed through its coma and was filtered by the gases there, revealed not just the presence of specific molecules, but also their relative abundances. And these abundances can be compared to theoretical models of comet composition to test our understanding of how comets form and evolve, and the fact that 2I divided by Borisov's composition was similar to but subtly different from solar system comets is exactly what one would expect if the same basic physical and chemical processes operate throughout the galaxy, but with variations in parameters like temperature and density, and elemental abundances that reflect local conditions in each protoplanetary disk. The question of whether there is life elsewhere in the galaxy is deeply connected to the study of interstellar objects, because these objects represent one possible mechanism for transporting organic molecules or even viable organisms between stellar systems. And while the panspermia hypothesis remains controversial and difficult to test, the existence of interstellar objects makes it at least plausible that material from one planetary system could end up in another. And if we could identify organic molecules of extraterrestrial origin in such objects, it would be a significant step toward understanding the distribution of life's building blocks throughout the galaxy. The rotation period of 2I divided by Borisov was not as precisely determined as that of Oumuamua, because the comet's activity in coma complicated the light curve, made it harder to see the periodic variations caused by rotation. But from the observations that were made, it appears that 2I divided by Borisov was rotating with a period of perhaps 7 to 10 hours, fairly typical for a small body in the solar system. And this similarity in rotation period is another piece of evidence that interstellar comets are not fundamentally different from solar system comets, that they form and behave according to the same principles, even though they were born around different stars. The moment when each object was first detected was not immediately recognized as special. The initial detection just flagged a new moving object in the sky, something that happens thousands of times per day in modern sky surveys. And it was only after follow-up observations and orbital calculations that the interstellar nature of each object became clear, and this delay between detection and recognition is typical of astronomical discovery, where the significance of an observation often only becomes apparent after analysis and context and comparison with other data, and this is why automated survey telescopes are coupled with rapid follow-up capabilities and sophisticated analysis pipelines that can quickly identify interesting objects and alert the community to their presence. The texture of the surfaces of Oumuamua and 2I divided by Borisov, whether they are smooth or rough or cratered, cannot be determined from the available observations, because we never resolve the objects as anything more than points of light. But we can make educated guesses based on what we know about similar objects in the solar system. Asteroid and comet surfaces tend to be rough and irregular, covered in rocks and boulders and layers of fine dust, and we would expect interstellar objects to be similar unless they have been processed in ways that smooth their surfaces, perhaps through repeated passages near stars that cause sublimation and redeposition of materials. The challenge of communicating scientific uncertainty to the public is well illustrated by the coverage of these objects. Scientists were careful to present their findings in terms of probabilities and confidence intervals and alternative hypotheses, but media coverage often simplified this nuance into binary statements about what the objects were or were not. And this disconnect between scientific communication, which is always tentative and conditional, and public communication, which often seeks definitive answers, is a perennial challenge in science journalism and science communication more broadly, and finding ways to preserve nuance while still engaging public interest is an ongoing effort. The gravitational focusing effect of the Sun means that interstellar objects passing through the solar system are actually slightly more likely to pass near Earth than one would calculate based on geometry alone, because the Sun's gravity bends their trajectories inward, increasing the cross-section for encounters with inner solar system planets, and this effect is small but measurable, and it means that observations of interstellar objects from Earth provide a slightly biased sample of the population, biased toward objects whose trajectories brought them into the inner solar system, where our telescopes are concentrated. And correcting for this bias is important when trying to estimate the total density of interstellar objects in our region of the galaxy. The symmetry between what we send out and what we receive is worth contemplating. Just as we are now detecting objects ejected from other planetary systems, some planetary systems around other stars are presumably detecting objects ejected from our solar system, objects that were flung into interstellar space by gravitational interactions with Jupiter or Saturn millions or billions of years ago, and that are now passing through those distant systems. And some alien astronomer may be observing one of our comets or asteroids right now and marveling at this visitor from a distant star. And this symmetry is aesthetically pleasing, suggests a kind of reciprocity, a mutual exchange of visitors that connects all stellar systems in a vast galactic network. The end of the observational campaigns for both objects was bittersweet, as each object faded into the distance and dropped below the detection threshold of even the most powerful telescopes. There was a sense of loss, a recognition that a unique opportunity was passing, that we would never see these specific objects again, and coupled with that loss was gratitude for what had been learned and anticipation for what would come next, for the next interstellar visitor that would surely arrive in time. And this cycle of discovery and loss and anticipation is characteristic of astronomy, where we study objects that are often unique, often fleeting, and where each observation is precious because it may be the last. The organic molecules that likely cover the surface of Oumuamua, formed from the irradiation of simpler ices by cosmic rays during its long journey through interstellar space, are of interest to astrobiologists because these molecules represent a possible source of prebiotic chemistry, the complex organic compounds that might have been necessary for the origin of life. And if such molecules are common on interstellar objects, and if such objects frequently collide with planets, then this represents a delivery mechanism for organic materials to planetary surfaces, a way to seed young planets with the chemical ingredients needed for life to emerge. And while we do not know whether this actually happened on Earth, the fact that the mechanism exists and operates throughout the galaxy makes it a possibility worth considering. The human tendency to anthropomorphize, to assign human-like qualities and intentions to non-human entities, is evident in some of the discourse around these objects. People speak of Oumuamua as if it chose to visit us, as if it has agency or purpose. And while this is poetic license and no one seriously believes the object has consciousness, the language we use reveals our deep-seated need to find meaning and narrative in natural phenomena. I tell stories about the cosmos that help us make sense of our observations, and this storytelling impulse is not separate from science but is in some ways the foundation of it. The human capacity to observe patterns and construct explanations and communicate those explanations to others through narratives that are compelling and memorable. The orbital inclination of interstellar objects, the angle between their trajectories and the plane of the solar system, can vary widely. Some might come in nearly perpendicular to the ecliptic, while others might be more aligned with it. And the distribution of inclinations in the population of detected objects can tell us something about the kinematics of the local stellar population, about how stellar velocities are distributed in 3 dimensions. And eventually, with a large enough sample, we might be able to use interstellar objects as tracers of galactic structure and dynamics, as probes of the velocity distribution of the interstellar medium in ways that complement and extend what we can learn from stellar observations. The fact that 2 different telescopes using 2 different search strategies both detected interstellar objects within a few years of each other suggests that the detection rate is likely to increase as more telescopes come online and as existing telescopes improve their sensitivity and cadence. And within the next decade, we will probably transition from a regime where each interstellar object is a major event warranting dedicated observing campaigns to a regime where such objects are detected routinely and can be studied systematically as a population. And this transition will bring new opportunities and new challenges. Will require new infrastructure for coordinating observations and analyzing data, but will ultimately give us a much richer understanding of the interstellar environment. The legacy of these objects will be measured not just in the scientific papers they generated, but in the inspiration they provided to young people considering careers in astronomy, in the public conversations they sparked about the search for life elsewhere in the universe, in the mission concepts they inspired, and in the way they reminded us that we live in a universe full of surprises, where the unexpected can arrive at any moment in the form of a faint dot moving against the stars, and where patient observation and careful analysis can reveal wonders that were previously unimaginable. And in this way, these 2 visitors, Oumuamua And the object we might call 3I divided by Atlas or 2I divided by Borisov, depending on which story we are telling, have already secured their place in the history of astronomy, have already justified the centuries of work that went into building the telescopes and developing the techniques that made their detection possible. And so we come to the end of this particular story, though of course it is not really an ending but a pause, a moment to reflect on what has passed before the next chapter begins. And that next chapter is already being written, is being written every night as telescopes scan the sky, looking for the next visitor. And when that visitor arrives, as it surely will, we will be ready. We'll have learned from these first encounters. We'll have refined our techniques and built better instruments and developed a deeper understanding of what to look for and how to study it. And each new interstellar object will add to the picture we are building of the galaxy beyond our solar system, of the diversity of planetary systems and the processes that connect them, and of our own place in this vast cosmic ecosystem where matter and energy flow ceaselessly between the stars, where nothing is truly isolated, where visitors from distant suns pass through our neighborhood carrying with them stories written in chemistry and physics, stories we are learning to read, slowly, patiently, one faint point of light at a time. And in this reading we find not just knowledge but wonder, not just data but meaning, not just information about the universe but insight into ourselves, into why we look up at the night sky and feel moved by its vastness, why we build telescopes and calculate orbits and stay up late analyzing images of objects we will never visit, why we care so deeply about these cold rocks tumbling through the darkness, and perhaps the answer is that in studying them we are studying ourselves, are exploring the question of what it means to be a conscious being in a universe that appears to be largely indifferent to consciousness, are seeking connection in the silence, are reaching out across the void toward anything that might reach back, and even though these objects do not reach back, even though they are inert and indifferent and governed only by the blind laws of physics, still they connect us to the rest of the galaxy. Still they tell us we are not alone, even if we are the only ones listening. Still they remind us that we are made of star stuff just as they are, that we share a common origin in the molecular clouds that gave birth to our sun and countless others, that we are all children of the same ancient cosmos, and that the universe may be vast and cold and indifferent, but it is also beautiful and full of wonders that arrive unbidden, that ask nothing of us except that we notice, that we pay attention, that we wonder. And in wondering perhaps we find something like meaning, something like purpose, something like home in the endless dark between the stars, where these visitors tumble patiently, eternally, carrying with them the whisper of other worlds, the ghost of other suns, and the promise that we are, all of us, everywhere, forever, connected by the slow dance of matter through space and time, spinning together in this galaxy we call home.